Hi, in this video we're going to be discussing the gamma distribution. So this is the end of section 4.4, so the last video, or second to last I should say. I'd like to do an example in this section as well, but this will wrap up section 4.4 though. And finally this gamma distribution. So what is the gamma distribution? So a continuous random variable x has a gamma distribution if the PDF of x is given as follows. F of x with parameters alpha and beta is the piecewise defined function given as follows. So in the last video we talked about the gamma function, and so we can see the gamma shows up here and the numerator looks very much like the gamma function except for the integral. So that will be important, and we'll come back to that this in fact defines a PDF, and most certainly this function is non-negative, because if we look, 0 is non-negative, and also any value of x given that it's positive will make this expression non-negative. So it should also be noted alpha and beta are greater than 0. Okay, so that means that this exponent here is in fact negative, and this part in the denominator is also non-negative. Okay, so what will be very helpful for us is the standard gamma distribution. So this is analogous to the standard normal distribution. So for us, it's the standard gamma distribution. And what is that? Has PDF with only one parameter, alpha, which is the gamma distribution, or the PDF of a gamma distribution with parameters alpha, but beta is equal to 1, which is equal to the following. This piecewise defined function. So notice that what is the correlation between the gamma distribution and the exponential distribution? Well, if we notice that, we have the following. So for alpha equals 1 and beta equals 1 over lambda, is the following. But with a little bit of algebra, we can see that this quickly simplifies to the exponential distribution. So let me slide up just a little bit here. So what can we conclude from this is that the gamma distribution is a generalization of an exponential distribution. In other words, anything that is an exponential distribution is a gamma distribution, particularly with the parameters alpha equals 1 and beta equals 1 over lambda. So our first theorem is that this function with parameters alpha and beta in fact defines a PDF. So the function defined by the gamma distribution in fact defines a PDF. So to see that this is a proof, or to see the proof of this, we've already verified that this function is in fact non-negative. So we don't have to worry about that. The only thing that we need to show now is that the integral from negative infinity to infinity is equal to 1. But by definition, this function, which I'll bring it back up, which is defined in the following way, is this value for only values of x bigger than or equal to 0. So in other words, the positive real numbers, so the positive real number line is what's called the support of this function. This function is 0 on the negative part of the real number line. So therefore, this integral reduces to just the integral from 0 to infinity. Just like so. So there's a lot of letters here, so it's not to get confused. The only variable of integration is x. All the other letters are constants or parameters, if you'd like. And so we're free to pull those out, group them however we like. So to do a little bit of algebra here, we can pull out the 1 over gamma of alpha. And we're going to group things in such a way. So in the denominator, we have alpha b's, if you'd like. So alpha need not be an integer, but still we're going to group alpha minus 1 of the betas with the x's to give us the following. And then the remaining beta, we're going to group with the dx. There's a reason for this. So setting all this up, we're actually setting ourselves up for a u substitution. So how are we going to do this? We're going to let u be equal to x over beta. Just like so. So u equals x over beta, du is equal to dx over beta. Inserting these pieces into the following integrand, we get okay, so this is very close to the gamma function. In fact, it is exactly the gamma function once we determine what these bounds are. So under this substitution, when x equals 0, u is still equal to 0. And when x goes to infinity, u also goes to infinity because remember, beta is a positive number. So by definition, this is in fact gamma of alpha. Now remember, the gamma function we thought of as an integral with, I believe the argument was x, but your variable of integration is irrelevant to the gamma function. I could call the same thing x if I'd like, or I could call y, whatever variable you'd like to use. Okay? And so therefore, this is just gamma of alpha by definition, that integral here, which is therefore equal to 1. So this is in fact a PDF. We'd like to state a few things about this. And I will give this as a theorem without proof. So sometimes I use this notation. What it means is that a random variable was never equal to its PDF, but has a PDF. So in other words, I'm saying x has the PDF given as follows. In other words, x, capital X, is a random variable with a gamma distribution with parameters alpha and beta. Then it follows that the expectation of x given mu given as follows. So these formulas are actually not terribly hard to derive, but I'm not going to do that here for the sake of time. You can go ahead and by direct definition, the direct definition of expectation, and using your variance shortcut formulas, you're able to derive both of these results. But the key here is to notice the following. And this will be important for us, is that in many of the applications that we'll see, these two formulas are very helpful. Once you figure out alpha and beta, you can figure out quite a few things. So in the normal distribution, all we needed was mu and sigma. And we're able to use the standard normal distribution to answer any sort of questions that we have using tables. Well, you'd like to use tables for the gamma distribution as well, but usually in the problem, you're given the mean and the standard deviation, or the mean and the variance of some gamma distribution. From this information, you then need the parameters alpha and beta in order to answer any questions about it. So these two formulas will be very helpful, and we'll come back to these in the next video. Another important construct is the CDF, or the cumulative distribution function, for the standard gamma distribution. In other words, by definition, this is the integral from negative infinity up to the value of x. Given like so. So just to point out, we are not using x anymore as the variable of integration because x is in the upper bound here. So this inside here is just our standard gamma distribution as follows. And we have tables for this. And so this is, by definition of the standard gamma distribution, this is just y to the alpha minus 1 just like so. And this thing also has a name. It's called the incomplete gamma function. And actually, incomplete gamma function up to constant. Because if we factored this out, you get something very close to the gamma function, but not quite, because it's not 0 to infinity, it's 0 up to x. So it's just part of the positive number line here. So we call that the incomplete gamma function. And we have a table for these values. So using a table, you give an x and an alpha value, and in the next video we'll talk about using that table in order to evaluate our incomplete gamma function for various values of x and alpha. So like the standard normal distribution related to the normal distribution, there's a way to go from any gamma distribution to the standard gamma distribution. Or better yet, the CDF, the CDF of any gamma distribution can be related to the CDF of the standard normal gamma distribution in the following way. As follows. So this is an important theorem for us because what this says is that in this we can go from, you give me parameters alpha and beta, then by this transformation we can use the standard gamma, or the incomplete gamma function table, to evaluate values over on the right hand side of this equation. So using that table, we can then talk about values for any gamma distribution where we have alpha and beta as follows. So to see how this works, we just start with the left and work our way to the right. Okay, so from here, we want to work where our argument was x, we want to get to x over beta. So we're going to use the same method as before. We're going to group alpha minus one of the betas with the y's and the remaining beta with the dy. And we're actually just going to leave gamma of alpha sitting inside there. Okay, gamma of alpha sitting inside here. So it looks like the following. You can verify algebraically that this integrand is the same as this integrand. Just the betas have been split up and associated with different terms. So alpha minus one of those betas are with the y, and the remaining beta is with the dy. So we're setting up for another u substitution. So here we're again going to let u be equal to y over beta. So therefore du is dy over beta. So the same substitution as before, leaving us in the following way. just like so. So this is very much like the standard, the CDF or the standard gamma distribution. So in other words, this thing on the right. But unlike before, where we did this trick to verify that this inside here is actually a PDF, our bounds do not stay the same. They're not from 0 to x. Now the bottom one is. So when y is equal to 0, u is also equal to 0. Top bound changes. When y is equal to x, u is equal to x over beta. So therefore the upper bound becomes x over beta, like so. And by definition, this is the incomplete gamma function evaluated at x over beta. Just like so. Okay, so that concludes this video. In the next video, I would like to use these results to do an example from the homework.